All right, welcome back. In this video, we're going to talk about levers. Levers are a rigid bar used to, as you can see on the screen, exert a pressure or sustain a weight at one point of its length by the application of a force at a second point and turning on a fulcrum at a third. So at some point within a lever, you're always going to have some kind of an arm or a bar. You will have a fulcrum that you rotate around, and then you have forces acting on them. There are three pictures of levers here because we have three distinct types of levers that we're going to discuss. The first type of lever is a first-class lever. With this, the fulcrum is always located in between the effort force and the resistance forces. So you can see these pictures. The fulcrum here, this is kind of your typical teeter-totter view right here, where your fulcrum is halfway between, or it looks like it is. But you also can have a fulcrum slightly towards your effort or slightly towards your resistance. And because of this, the first class lever is the only class of lever that can have a mechanical advantage that's both greater than or less than 1, or equal to 1, I guess, as well. So the first class lever gives you a lot of different options. The second class lever is where the fulcrum is located toward the end of the lever. I mean, it says it's at the end, but technically you probably could have a lever arm that extends this way somewhere. But your fulcrum is somewhere towards the end, and then your effort and resistance are both on one side of the fulcrum. And with a second class lever, the resistance force is between the effort force and the fulcrum. So you have the effort force outside, then it's the resistance force, then it is the fulcrum. So with a second class lever, because of how math works with your distance, so if we remember, IMA is equal to dE over dr. Well, dE must always be bigger than dr because it's outside of that. So in this case, our mechanical advantage is always greater than 1. If we have a third class lever, it's the same setup. Again, you could have a little bar extending out here, but this time your resistance force is on the outside and your effort force is between the resistance and your fulcrum. So again, IMA is equal to dE over dr. Well, if dE right here, distance effort, distance resistance, if dE is always less than dr, then that means this fraction right here is always going to be less than 1. So a third class lever always has a mechanical advantage of less than 1. The concept of a lever and the way it works is because we are using moments, okay? The turning effect of a force about a point equal to the magnitude of the force times the perpendicular distance from the point to the line of action from the force. That's a wordy way of saying I have a force acting down. My lever arm is acting horizontally. This force is exactly perpendicular, as is this force, and the fulcrum is here. So let's say that this is a distance d, this is a force F, a moment is equal to the distance times the force. That's what they're saying in that little paragraph there. But the key here, where we talked about work earlier, work was a parallel distance where the force was acting parallel to your arm. In this case, it's not. It's acting perpendicular to your lever arm. And so this would be a perpendicular distance times your force, giving you a moment. Why is this important? Well, if you think back, and if you watched my other video talking about mechanical advantage, we have AMA and IMA that are working together for mechanical advantages. So I'm going to skip ahead here, and then we'll come back and talk about this. But AMA and IMA are important because the concept of levers and how we can solve for things later is all based around rotational equilibrium. And when it comes to simple machines, what does that mean for us? It means that AMA is equal to IMA. So if I remember, AMA is FR divided by FE is equal to IMA, which is DE divided by DR. if I rearrange this, in math, if you remember cross multiply, right? I could rearrange this equation and I could say FR times dr, make them both the same. FR times dr, look, force times the distance, that's a moment, is equal to FE times DE, also a moment. So moments are the basis of everything, and that's why it's important to realize that moments are what make simple machines work. Okay, so I'm going to go back. I'm skipping over some stuff. The twisting force that produces rotation caused by a moment is called torque. So we'll just throw that in there. And if you look at the example here, we need the effort moment acting on a lever. So the moment of our effort would be the force of effort times the distance of effort. In this case, it would be 15 times 5.5, and let's let them do the work for me. So 15 times 5.5 is 82.5. And when you write it, you write both units, so I'm multiplying inches times pounds, so I write it as inch pounds is how you would write that moment. All right? So that's, in a nutshell, a little bit of a combination of both levers and how levers work, and then also the concept of rotational equilibrium, which we're going to need when we start talking about our practice problems a little bit later. But I'm going to leave it right there for now. So come back and follow along with my next video. I'm going to talk a couple videos about, I'll have a few videos about wheel and axles and pulleys, but I'll also have some example problems that I'll be sharing with you as well.